Hello, I'm Katrina.
And I'm Kiana.
And welcome to our tutorial on optimization.
To start out with, what is optimization?
Good question, Kiana. Well, imagine that you're given a certain amount of fencing. Your goal is to set up the fence in such a way that you have the most area in between the fence. By relating several formulas and using calculus, you can optimize the area within the fencing.
Some other examples in which you might rely on optimization include maximum profits when considering revenue and cost, or the area enclosed by a box with a set amount of surface area. Keep in mind though that optimization doesn't only mean that you are looking for a maximum solution, but you might be looking for a minimum as well.
Anyways, let's get started with a basic problem. Say that we have a rectangular fence that we have to build, and we want the most area enclosed by it possible. We are given 30 feet of fencing to work with. For this problem, I know that the area has to be rectangular, so I would draw this feature. I would then label my picture with variables. These sides have the same variables since they always have to be the same, and these sides as well. Next, in order to come up with a formula for this problem, I would consider the factors involved. Since I know I can only use 30 feet of fencing, I would say 2x plus 2y equals 30. Then, since I know that I'm solving for area, I would say x times y equals area.
Next, the two equations must be related. Using the equation 2x plus 2y equals 30, we can solve for either one of the variables and then plug into the go. The reason we are plugging into the area formula is because we are looking for an optimized area. After relating the two equations, we find the derivative in order to solve for the critical point.
Remember that critical points include endpoints, so we must take into consideration y equals 0 and y equals 15. Now that we have a set of variables, we can figure out which one gives us the answer we want. Since two of the sets give us an answer of 0, we know we can throw those out since we obviously don't want an area of 0. That leaves us with 7.5 by 7.5. So in solving optimization problems, use the steps that we use to solve this problem. Number 1, understand the problem. Number 2, draw a picture and label it with variables. Number 3, use the variables to come up with formulas considering all of the factors involved in the problem. Number 4, relate the formulas by plugging in a variable. In other words, solve for one variable and plug it into the formula that you're looking for the answer for. Number 5, find critical points by using the derivative. Remember to check endpoints. Number 6, use to solve for remaining variables. Plug your answer into the original formula to solve for the other variables. And final step, find out which set of variables gives you your desired answer, whether it be a maximum or minimum. Now, to make sure you have the point, let's apply these steps to a more complicated problem. Number 1, understand the problem. Let's pretend you are given a cardboard square in which you have to cut each corner off so that you can fold it into a box. This open-faced box should have the most area possible. Find the dimensions of this box. Now that we have completed the first step, we can go on to step number 2, or draw a picture with variables. Since I knew that I needed a square with each corner cut, I drew a square with each of its corners missing. The new box should have a side of 8 minus 2x, which I can tell by looking at my picture. The length of each corner cut off will be x, and all the corners should stay the same. Now that we have drawn a picture, the next step is use the variables to write formulas. I know in this problem that I'm looking for volume, so I will use this picture to write a formula for volume. I know that volume equals base times height, and in this case, the base is 8 minus 2x times 8 minus 2x. And the height of the box will be x. You can tell, since by folding this box, the base will be this area, or 8 minus 2x times 8 minus 2x. And the height will be the folded in area, or x. The next step is relate the formulas by plugging in a variable. However, as you can tell, we only have one formula for this problem, and since we're looking for volume, we really don't need relating. In the next step, we need to use the derivative to find critical points. So now we are left with two critical points, 4/3 and 4. The next step is use the critical points to solve for remaining variables. However, since we have no remaining variables, we can ignore this step and move on. And the final step, find out which set of variables gives you your desired answer, whether it's a maximum or minimum. Since one of our critical points gives us an answer of 0, and the other gives us an answer of 37.9, and we're looking for the maximum volume, we know that 4/3 is our answer.
How do you know which critical points give you the final answer?
Basically, you have to plug in all the critical points, including endpoints, back into the original formula. If you're looking for a maximum, obviously your answer is the one that gives you the biggest quantity. And if you're looking for a minimum, you obviously choose the smallest quantity. So choose whichever endpoint gives you the answer you're looking for, considering the parameters. So how do you know when you're solving for an optimization problem?
Generally, when you're looking for a maximum or a minimum and you have a set of restrictions, it's when you're solving for an optimization problem.
Alright, one more time, let's review the steps necessary to solve an optimization problem. Number 1, understand the problem. Number 2, draw a picture with variables. Number 3, use the variables to write formulas. Number 4, relate the formulas by plugging in a variable. Number 5, find critical points by using the derivative. Number 6, use the critical points, including endpoints, to solve for remaining variables. And the final step, find out which set of variables gives you your desired answer, whether it's a maximum or minimum.